Good afternoon, everyone. Thank you for joining for this webinar, which the topic we have decided is the optimize the fluid and thermal performance of a product. Today, we are joined by our speaker, Mr. Pratik Deshpande, who will be delivering this webinar. Pratik is a CAE analyst with master's degree in mechanical engineering from New Jersey Institute of Technology, New Jersey. At EDS Technologies, Pratik is responsible for technical initiatives for SIMULIA across industry segments. He works very closely with strategic customers, understanding their design requirements, and provides specific workflows with SIMULIA products on mechanisms, FSI, vibration, co-simulation, fatigue, and failure models. He had worked with Detroit Engineered Products, Michigan as an applications engineer and as CAE lead research engineer with Lightweight Manufacturing Systems Department of General Motors. Before handing over the session to Mr. Pratik, I would like to request the audience if they have any questions during the course of the webinar, they can enter it in the question box. We will take it up at the Q&A session at the end of the webinar. Over to you, Pratik.
Thank you, Abhay. Thank you for such a nice introduction. And good afternoon, everyone. And welcome to today's webinar on the Fluid Dynamics Engineer role, which is available on our 3D Experience platform. And how even at the designer level, we can leverage the capabilities use this particular role for the better development of our products. To start with a little bit on about EDS Technologies. So EDS Technologies was incorporated in 1994 and we are celebrating our 27th year. And we are platinum partner to Dassault Systems, and we are one of the largest engineering solutions providers in India with over 1700 plus active customers that we are currently helping as well as supporting. We have about 7 offices across India as well as dedicated sales, support, marketing, pre-sales team. And apart from Dassault Systems, we also have partnered with multiple different OEMs like Technia, EOS, 3D printing or additive manufacturing machines, Synopsys, ISRI, Festo, DEP, Presages, Human Solutions, as well as Mac Technologies. Now, to start with my presentation, so these are the topics that will be covered through the course of this webinar. So to start with, we'll start with 3D Experience platform, then CFD for designers, or how designers in the initial or the concept level, can leverage the fluid dynamic capability which is available onto the 3D Experience platform. Then we will move on to the core capabilities of the fluid dynamics engineer role, as well as automated design exploration and generative design, which is Tosca based for our non-parametric optimization. And finally, a few examples from the automotive domain to showcase, how you can use it for your day-to-day applications. So to starting with 3D Experience platform. So 3D Experience platform provides a unique collaborative environment. It adopts a single geometric modeler user interface, input, output, and security model. The design, engineering, and simulation apps operate on the platform without the need to export and translate the files. Like I was saying, so, onto the 3D Experience platform, whether it is design or whether it is engineering and simulation, these are available in the form of roles and applications, which can be fired anytime the user needs them. And I do not have to switch from one application into another application, because it's a single unified user interface experience that as a user you'll give. And one of the advantage of this is the data is always live, and you can either have the platform on premises or on cloud as per your requirements. And on top of that, we can have a collaborative business platform. It's a single, easy to use interface, common access as a user. I'll have a common access to multiple disciplines, be it design, be it simulation, be it manufacturing, business intelligence, project management, many more. Likewise, many different capabilities are available. Now, again, the 3D Experience platform is also available on premise or on cloud as per your requirement. Now, these are the key values of the 3D experience platform. So like I said in my previous slide, we have unified user experience across all processes as well as all industries. And we also have extension to any discipline. It can be engineering, manufacturing, sales, marketing, procurement, finance, business dashboarding, with a view aggregating multiple data sources for any discipline. It can be your manufacturing plant, or it can be your design or simulation team. And it's also designed for the cloud, enabling fast deployment to SMBs as well as new industries. And all the different roles and the applications and capabilities that are available, these are packaged by the processes built from customer needs as per the industry standards, as well as we have openness enabling integration of customer data in one single environment. So here you are accessing the platform from your workstation as an example. Now note here that the look and the feel, whether you access from a browser or as rich application, is exactly the same. So whether I am using it from the browser or whether I have installed the 3D experience platform, the experience for me to use the application will remain the same. And we also have a search feature called as the 6W tags to sort through a ton of data that could have been generated by product design teams. And you can also sort through materials. You can also view and sort simulations that have been created by the users. You can also go over all the CAD as well as design data. And if you want to review a particular product, say in this case the design data for a motorbike, you can simply explore it on a turntable. This way, you could have a very concise view of the entire product design. You can also use business essential tools to review your design data. You can view if particular parts or assemblies have been properly updated by the respective teams or not. And if you see if some components have a newer version available, you can even review what simulations are particularly associated with the product. And in this case, you could see that there are 3 different products simulations for the product. So now, to start with the actual fluid dynamics, we'll start with the CFD for designers. And as you can see, onto my slide, Dassault Systèmes SIMULIA is a brand under which we have realistic simulation tools that are available. So we have a set of tools for performing structural validation like Abacus. For design of experiments, we have EyeSight. For non-parametric optimization, we have Tosca. For durability as well as fatigue, we have FESafe. For multi-body simulations or MBDs, we have SIMPAC. For fluid dynamics, we have a fluid dynamics engineer role. We also have a CST suite for the electromagnetics. We have NVH. For NVH, we have Wave 6, as well as we have XFlow and PowerFlow for highly advanced aerodynamics as well as computational fluid dynamics. And these are driven by 3 complementary technologies, especially when it comes to the fluid dynamics engineer, which we are going to focus and talk today on. These are driven by their major technologies inside the Dassault Systèmes, that is XFlow and PowerFlow and mainstream CFD onto the 3D experience platform, which will enable multi-scale, multi-physical vision of integrating CFD with design, simulation, optimization, data management, as well as business intelligent applications, which is again all available and can be performed within the 3D experience platform environment. And by doing so, I'll be able to deliver high value end-to-end solutions through industry processes on the 3D experience platform. Now, if you see, this is the fluid dynamics engineer role, a brief wherein it involves a regular structural validity. I have a computational fluid dynamics application. I can perform design of experiments. And at the topmost, you can see there are multiple designs. This is through the generative design feature. And what I can do with the fluid dynamics engineer role, I can have accelerated design iteration, and it can have both CAD as well as PLM embedded computational fluid dynamics. On top of that, one major advantage is we have a guided user interface, which is going to guide me as a user throughout the whole pre-processing process to make sure that whatever pre-processing I am doing is proper and it is validated by the for the CFD processes. And on top of that, we have automatic meshing, wherein as a user, I do not have to worry about the wetted surface extraction or how should I extract it and what type of mesh should I use. Everything is automatically taken care by the rule itself. And we also have automated design exploration. So we can create DOE loops or design of experiment loops. We have design space optimization, analytics driven decision support, and we can validate for accurately capturing the designer workflows. So whether it is steady state and long transient simulations, whether it is heat transfer, whether it is thermal simulation, or even conjugate heat transfer, including laminar as well as turbulent flow modeling capabilities, are all available with the fluid dynamics engineer role. And we have been using a lot of term called as unified. So I have unified user experience, I have unified multi-scale, multi-physics design environment. The reason we are using this particular word unified is because, like I previously said, whether I am using a CAD role, whether I am using a structural validation role, or for that sake, or for this discussion's sake, if I'm using a CFD role, the GUI and the user assistant remains the same, and the user assistant is going to assist you throughout the whole process and giving you the same feeling of the user interface, as well as seamless integrity between your CAD, PLM, as well as the finite element model. And because of this, I can capture multidisciplinary requirements. It can be fluid structure interaction, it can be 3D CFD, it can be 1D simulation, and all this is possible through the 3D experience platform fluid dynamics engineer role. Now, as an example here, you see, this is one of the CFD workflow onto the 3D experience platform for a exhaust flow performance. So we start with the inputs. So we have operating conditions, we have engine exhaust, mass flow rate and temperature. We also have catalyzer properties and the native geometry. Then onto the 3D experience platform itself, we do the model preparation. So again, as compared to the standard process of model preparation, wherein I take in the CAD, I have to clean up the CAD geometry, then I try to extract the wetted surface, or you generate the wetted surface to carry out the computational fluid dynamics. Onto the 3D experience platform, I do not have to worry so much on all these initial steps, because 3D experience platform is smart enough to take care of all this the moment a native geometry is imported. So during the model preparation, I'm just going to assign what would be the part, if it is an assembly, what would be the part that I am interested for carrying out the CFD study. So that is what is under the model preparation. Then we specify the operating scenario. What would be my input? What would be my output? My material properties, my loads and boundary conditions, etc. Then there is an automatic body fitted mesh, which again 3D experience platform does. And even though it is automated, as a user, you still have the freedom to choose the element size. If you want to change the density of mesh in a confined boundary, you can also do that. And once that is done, we go to the job execution. We submit the run. You can submit it on your premise computer, or you can submit it onto the cloud, whichever option you feel feasible for you. And then result post processing, and based on the results, I can improve the design right there and there itself by invoking the different roles which is available to me. It can be design of experiments, it can be generative design powered by Tosca, and the outputs after following the whole workflow would be optimal design. And in this particular case study, we were interested into the flow velocity as well as temperature, which was taken out, as well as the pressure profile and the delta P of the study. Now, I have said previously that by using this particular role, one of the major advantages is accelerated design iterations. And this is proved here by, I'm not sure if there is a video here. So let me show it to you. So turnaround time for the first run was about 28 minutes. And for the simulation setup, it took us to about 15 minutes. And once the setup was done, to mesh and solve, that is computing the results, it took about 3 minutes, as well as to extract the key results, it was 10 minutes. So overall, from simulation setup up to extract the key results, it took us about half an hour. And the example which here again was considered was an exhaust flow performance. And the key KPI was to minimize the pressure drop. That was the objective. And you also have certain information at the bottom of the slide which says mesh size that was used was about 256,000 elements. We used about 8 core computer capability to perform this analysis, and it took about 411 iterations to converge to the solutions, and it was a steady, incompressible, no conjugated heat transfer study. So I have a small video which showcase how everything was set up, and while you are looking at the video or the demo, on the right hand side you can see the user assistant, and also you can see each and every option under the user assistant is been marked by a red circle. What exactly it means? That either the model, the physics, or the initial conditions have not been set up, or if say I have set it up and I have set it up in a wrong way, then it displays it in red color. So once everything is properly set up, obviously at the bottom of the assistant you see there is fluid domain, there is fluid section, which also gives a small note on what exactly that option will do. So once I do it correctly, you can see the option from red circle is going to change to a green check mark or a green square box, meaning proper conditions have been assigned for a given model. So now we are creating a fluid section to showcase what would be the to assign air and porous media properties, as well as what would be my inlet and outlet. And also onto the 3D experience platform, unlike Abacus standalone, we do have a material palette wherein you have access to about 3,000-4,000 materials. And on top of that, if there are some materials which is not available into the palette, or you want to make certain changes, you want to add some new properties, you can add it and you can save it in the database. And like Abhay said, if you have any questions, please feel free to ask us in between, and we'll do best to give justice to those questions. So you can see now the model has been changed from red circle option to a green check mark. So now we are assigning the physics, that is it a steady state, is it a conjugated heat transfer, etc. And now the boundaries and loads and boundary condition, like what would be the mass flow inlet, pressure outlet. And then if there are any contacts can be assigned. If there are any zones can be assigned, like porous zone, substrate zone, etc. Where we are again assigning all the different properties, like viscous resistance in XYZ, inertial resistance in XYZ. And then we'll mesh it once this step is done, and then we'll simulate it. So of course, whatever is captured, this is not going to run for 28 minutes. So the simulation time we have cut it short so that you would be able to see the whole end-to-end process. So again, here the body fitted mesh, including the wetted surface region, and basically it's a hex dominated mesh that we can create. We can very much create it completely automatically and quickly. Now I'm going to simulate it. So once I click on simulate, that's when the tool is going to generate the mesh and then run the analysis. And you can see a plot of maximum convergence error versus increment. So I have different options under the plot variable too. And this will be the post-processing once the analysis is done. So these are the velocity vectors from the inlet towards the outlet. I have gauge pressure, I have absolute pressure. All these different outputs also can be captured very nicely with the high visualization result viewer that we have onto the 3D experience platform. You can cut sections to better understand how the system is performing inside. You can see the mesh with the geometry. You can create translucence. All these different options are available, which will make my job as a user much easier, and I can have better and accurate results. So these are the plot pressures. So this is the velocity again, gauge pressures. And see the velocity lines. Oh, sorry, gauge pressure lines. And you can see currently at the top, it says SIMULIA Physics Results Explorer. So that is the application for the viewer. So now coming to the core capabilities. So what we saw, or a little bit what I spoke previously, was from a designer point of view, wherein as a designer, he can quickly validate the CFD model. Now coming to the core capabilities. So what all capabilities are available inside the Fluid Dynamics Engineer, which is available on the 3D Experience platform. So I've already made some points here. So all these different capabilities, or physics coverage as we call, is possible and can be done through the Fluid Dynamics Engineer role, like steady state transient flows, laminar turbulent flows, incompressible and all speed compressible flows, Newtonian, non-Newtonian flows, multi-species and free surface flows, that is VOF, void, native conjugate heat transfer, surface to surface, as well as solar radiation, Joule heating coupled with electric field, intake, exhaust, conductive, porous media, multiple rotating frames, as well as multi-scale, multi-physical framework like fluid structure interaction, one-dimensional plus three-dimensional CFD combined, all can be performed here. Now coming to the solver, the core capabilities, so we have co-located finite volume scheme, wherein we can do segregated velocity pressure studies, coupled solvers we have, all speed compressible flow solver, unified implicit steady as well as transient. We also have conformal and non-conformal mesh support, again, which is automatic. We also have a gradient calculation for hybrid method, like weighted least squares or green Gauss linear exact formulation, which combines accuracy as well as the robustness. And coming to the time discretization, we have the L-stable time integration. We also have the three-step backward Euler. We have variable time step support, which is, again, all these solvers are highly efficient and robust. And in-house developed AMG linear solver for additive correlation algorithm, which will also help us for a faster setup and multi-grid cycles and reduce memory requirements. So an example also for the memory requirements is showcased here below. And turbulence modeling, when it comes to the core capability, the turbulence modeling, where we are using the Reynolds average Navier-Stokes RANS or eddy viscosity based turbulence model. And you can see, I'm not sure if I have a video. Okay. So then comes the meshing. Again, we said that we are having automated meshing capability, which is available into the Fluid Dynamics Engineer role. So with this capability, minimal user input is needed. Like I said, yes, up to a certain extent, if I want to change the mesh size, I can do that. I do have the freedom to do that. So apart from that, minimal input is required. And once we tell the tool to go ahead and mesh it, it's a highly robust meshing for complex geometries. And automatic fluid volume extraction, or the wetted surface as we normally call. We also have body fitted for high accuracy, which interfaces with multiple mesh types. And most of the times, almost more than 60% hexahedral elements are used, which will have reduced cell count versus the tetrahedral meshes. And we also have a good quality with low skewness, meaning whatever mesh I'm creating, the tool is smart enough to take care of the element quality criteria that will be required for a particular study. And there is a small video here, a small demo here on the meshing, so you can have, it's quite interesting. So this is one of the result of flow analysis. So this is the meshing tool. As you can see at the bottom, there are different options, and I have hex mesh. I can do a diagnosis of the mesh. So what the tool does is, if the elements are fitting the quality criteria, then under the diagnosis you will have a OK with a green square box, meaning all the meshes are fitting the mesh, or the elements that have been created are satisfying the given quality criteria, and I don't have to change or worry about the mesh, as it's not going to give me any problem during the solving. So this is the mesh that has been created. It's a gradient mesh, of course, as you can see, and it's always hex dominated, like I have been saying. and that's the bounding box under which the study will be carried out. So even for creating the bounding box, we do have the automatic option wherein I can input the dimensions in my X, Y, and Z, and the tool is going to automatically create the bounding box, and later on it's also going to mesh it as required. So moving on, again coming to the same core capabilities, I do have a few slides on the core capabilities. So this is one step. Tetrahedral mesh also is available, although we prefer hex dominated or hexahedral mesh. We do have one step tetrahedral mesh wherein automatic self mesh generation is possible. It is support for meshing solid as well as fluid parts. Boundary layer modeling is available, and this mesh also allows to load parameters from saved tetrahedron mesh rules, which I might have used previously for a different project. And automatic defeaturing capabilities are available here, wherein with a click of a button, you can simplify geometry. If there are any holes, you can fill the holes. If there are any fillets, you can defeature or defillet them. If logos are there, logos can be removed, all through a simple click of the button. And coming to the multiphysics or the multi-scale capabilities, so which is specifically the fluid structure interaction as well as the 1D plus 3D coupling. So we have seamless integration with Abacus structural solvers onto the 3D experience platform itself. So we do have roles which are basically the Abacus structural, which comes with Abacus structural solving capability. And when it comes to the meshing, again here into the CFD role itself, we have independent meshing for CFD as well as independent meshing for the structural simulations. And finally, these can be combined to have a combined results. And we also support, couple system, that is 1D models from Daimola. So Daimola is one of our another tool for 1D simulations, and that can be seamlessly integrated with the CFD within the platform to have a 1D 3D coupling CFD analysis, as well as implicit iterative coupling, which is controlled by the experiment creation app, wherein you can define and create different types of studies or different types of experiments using the experiment creation apps. And again, this particular the workflows that have been generated or created through the fluid dynamics engineer role are validated for accurately capturing the designer workflows. So this one is one of the examples of the manifold here. So we have an experimental flow set percentage and CFD flow split percentage, which was done inside the fluid dynamics engineer role on the 3D experience platform. And you can see the lateral duct experimental value was 24.8, whereas what we got through the 3D experience platform was 24.5. Similarly, the central duct, again 25.7 versus 25.3. Central duct on the right side, 26.1 versus 26.7, as well as lateral duct 23.4 versus 23.1. So we are trying to collaborate here with the lab results, and this is giving me the confidence to tell you that whatever analysis you're doing or going to do through the fluid dynamics engineer role is going to give you highly accurate results. So now coming a little bit to the automated design exploration. So, once we have the model, we identify the key parameters. So in this case, you can see the parameters which is highlighted in the bottom. So a few parameters that have been chosen here are, the inlet outlet, the diameter inlet, the diameter outlet, the radius, the inlet and the outlet radius, as well as the length of the duct, the size of the cross section, as well as the radius of the cross section. Then we do the initial simulation. We have to do an initial simulation to have the results with which the design exploration will refer and try to give us the optimized design. And then we define the process. In this scenario, it's about design of experiment loop, wherein we modify CAD parameter, we simulate it, we go back to the CAD, modify the parameter again, simulate it. We do it for a certain number of times so as to get the optimal results. And finally, we do a review performance analytics as well as trade-off to see out of those n number of designs that we have generated, which would be feasible to manufacture, keeping in mind the manufacturability or the castability or the machinability constraints. So all this again can be done throughout, and we finalize the design, and we can again, so whatever the process here I'm talking about, what we have done, we can save the workflow in the form of a template which can be used to reuse it again. We can even automate it, and we can democratize it throughout my team, so that the same quality of work is maintained, and the similar type of analysis now is not going to take me a lot of time. So a lot of time saving is done. At the same time, the computational cost is also reduced drastically, because I am simply reusing the workflow which has been already validated and saved it. And then platform also provides specific applications to analyze data that is being generated by the design of experiments. In this case, we ran a DOE with various geometric parameters, which we saw in the previous slide for the duct model, and we want to analyze the data and what configurations gives me a minimum pressure drop. So there is a small demo here to showcase, how this design of experiments was done onto the platform. So these are the different applications on the left hand side, as you can see. So you can use whichever is required for at a particular time rate. And this design of experiment works just like the eyesight. If anybody of you have used or known about eyesight, so the same eyesight capabilities have been extended onto the 3D experience platform, and the role to carry out this is called as the process composer, wherein I can pre-execute, post-execute, as well as execute options, wherein I can set up the model, run the design of experiments, and then validate the results. So the different parameters here have been given, and we will be running the design of experiments for the same parameters. Again, it's a drag and drop menu kind, where it's not going to take me a lot of time to set up the model as well. See the different parameters here. We also have given the values. And as you can see, we are creating different parameters for us to visualize later to choose out the best design. Now we are going to save the simulation and execute the simulation as well at the same time. So the different DOE techniques are available. We'll be using a full factorial technique in this case. So apart from full factorial, we have hypercube method, we have Latin hypercube options, and likewise, many different algorithms are available to carry out our design of experiments. So currently we are choosing about 4 parameters here, and we are trying to run, the different values. Or basically what process composer does is, it forms a matrix, and our objective here is to find the maximum as well as the minimum pressure. And now we are going to run the simulation. So we are just executing the current simulation process. So result analytics web app is another web app which will show us how to explore the results from the design of experiments, as well as we can answer the most common questions like what if or what is my best option, and we can post-process, visualize, and analyze trade-offs in a large data set. Not only that, the simulation process can also be deployed as a simulation experience with a simple to use interface in a web browser. The benefit here is that non-experts can set various parameters such as seating configuration, HVAC settings, cabin conditions from their web browser, and quickly run CFD simulation. Once the simulation is run, then we can review the results. So that was basically with the fully automated custom interface, which is available to the process composer or the parametric optimization tool, that is eyesight or process composer. Moving on to the generative design, which is Tosca based, and this is generally used for non-parametric optimization. So here, the key values are we can automatically generate designs for maximum flow performance. We can reduce the time up to 10 times turnaround time for fast-paced product development and digital continuity with a single unified application as opposed to multiple point solutions. Eliminating inefficient data transition can be achieved, as well as faster time to market with simulation-driven design enabling conceptual as well as detailed redesign phases. So as is workflow, especially if I go for a particular non-parametric optimization, it will take about 5 days. And you can see everything which is in light green color, those are the automatic process, and the dark blue ones are the manual process. So you see importing geometry is a manual process, import CFD model, it can be a third-party CFD tool, again is a manual process. Then creating Tosca fluid setup, if I'm using a standalone tool, it's again a manual process. Then optimizing flow field with Tosca fluid, it's going to be automatic because the tool does it. And again, computing flow fluid with third party can be again automatic. So basically, to complete this whole workflow all the way from create design space geometry to manually build manufacturable geometry around the optimized fluid shape usually takes us around 5 days. Now, with the 3D experience platform capability, which combining CFD with design of experiments as well as generative design, the 5-day activity was reduced to half a day, wherein only the first 2 steps, that is creating the design space geometry as well as defining setup for CFD and flow optimization in one single app, has been done manually. The rest, that is flow field computation, optimizing within one application, then extracting the elements from flow field based on user criteria, smoothing those out, validating the new design by doing some structural validation, and finally creating automatic geometry reconstruction is all automatic. And all this complete whole process can be completed in half a day without data translations, no application transitions, minimal user interfaces, as well as streamlined user experience and manufacturable ready designs. So the designs also that are created through this process, they pass the first test itself, wherein I can go ahead and manufacture the component right away. So this is one of the example of the generative design tool, how it works. So we are considering a casting block over here, and the fluid speed we have considered here is about 5 meters per second, and our target is to optimize the mass, and we are doing a fluid optimization. So, and the tool automatically eliminates the recirculation to improve the fluid performance, and any changes or design changes required for that, also the tool automatically creates. And you can see how it's removing material where it is necessary. And this is what the finally automatic shape generation is what we have got it, once we have done the optimization. So this is the new optimized duct design, and you can see the flow. There is no interference between the flow, and I have a very streamlined flow here as well. So that on the left hand side was the legacy part, on the right hand side was the generative design, and you can see how the performance also has been increased, as well as the pressure, 26% pressure drop was achieved. Now finally, a few of the automotive application examples to end the session on the fluid dynamics engineer role. So this is HVAC duct and mixer design. So this was done to explore the duct design and mixer performance across full range of climate control models. And you can see the different results onto the left hand side. You can see the flow velocities on the right hand side, and we can have you can see that we have a better streamlined flows onto the right hand side as well. And the other is the engine thermal design to improve the performance as well as fuel economy with efficient powertrain thermal management. So the engine was, the point of study over here. So the temperature, the maximum temperature at those two locations is about 475 degrees. So this is the gasket again. So everything, every study was done in a detailed way onto the whole engine as such. So this is the coolant temperature graph. Sure. So if you have any questions so far, please feel free to ask. And coming to the electric or hybrid motor thermal design, we also have an application, an example. This is to inspire vehicle electrification as well as hybridization with efficient thermal management. So previous case as well as this case, it was all about the thermal management studies, which can be done through the fluid dynamics engineer role. So we start with the CATIA assembly design, as you can see, for a concept stator motor, and also to study the cooling, the physics of cooling here. And again, I did forget to mention one point onto the 3D experience platform. So apart from the user assistant panel that is available, which is going to guide me as a user to set up the model, run the analysis, or post-process it, I also have a model tree on the left-hand side in the GUI, wherein all these different options again can be performed through the model tree as well. So with the ease of the, however the user finds it easy for him, he can either use the user assistant panel, or even he can use the model tree, to set up the model, to run the simulation, as well as to do the visualization or extract the results, once the analysis is completed. So one other example is a powertrain electronic thermal design. So here, to improve the power electronics reliability through better component placement and enhanced cooling. So it's not working video. So this another example is the exhaust system design. So previously I was talking about placement of the the components for optimal cooling. So we did work with one of our EV customer, wherein the engine, the electric motor was getting heated a lot, and by using the generative design approach, we were able to modify the design as well as place it in such a way that about 30 degrees of temperature reduction was possible, or we were able to achieve 30 degrees of temperature for that particular project. Then we also have exhaust system design to explore the catalyzer choices for maximizing exhaust line performance. Sorry, for some reason the video is not working. So these were some of the examples we have taken from some of our customers who are currently using the CFD tool onto the platform, and they are leveraging not just the CFD capability, but along with it, the design of experiments, the structural validation, as well as the generative design approach to optimize their product, to bring their product faster to the market, by at the same time making sure the components or the products are coming out with high quality as well as highly optimized, in turn saving them time as well as cost. So that's all from my side today, and thank you all.
Thank you everyone for attending our webinar, taking your time and attending this very insightful webinar on FMK role in the SIMULIA brand. So we'll be coming up with more such interactive, insightful sessions uh, from EDS Technologies. So please stay tuned to all our social media handles to check our upcoming sessions. Thank you.